Namaskar. I am Rudra Kafle from Worcester, Massachusetts. So this is a brand new episode of Physics is Fun, right? So today I am applying Newton's second law of motion or Newton's laws of motion in some brand new system, right, which we have not explored yet, right? So this is the spring mass system. So first I will do some demonstration and then I will explain the physics behind it. And also today I will be applying some technology that is digital technology. I will be explaining based on some online simulations. Okay, I hope this will help understand this new kind of system. Okay, so let me show you a quick demonstration, but before that let me ask you, why are spring systems interesting, or how are they useful? Where do we use them? So I have some gadgets here, some stops here, which are which show the everyday life use of spring, right? For example, so we use ball pens, right? So there is a spring inside here, right? So when I press down, the spring is compressed, right? The spring then pushes the lid out, so we can write, and then we can, if we want to bring it back, we press again, the spring extends and the lid comes back. Okay, so for example, I moved out the spring of here, so this does not work that way. So spring is a very useful system in a very simple device, the ball pen or a pencil. Okay, so just like in here, okay, you can see that. So when I push, there is a spring is compressed, right? Spring is compressed and the lid comes out. When I press again, the spring stretches, expands, and then the object comes back. Similarly, spring is used in toys. Let me show you a toy, right? So in this toy, if you see here, right, in this toy here, right, there is a spring system, right? So when I push it down, spring is compressed, right? When I released, the spring stretches and it has energy stored there, or it has, let's say, the force, and that pushes the object back. See, that is it has also a spring system. So these are toys and some other gadgets like I just showed you. But where else do we use spring? We use spring, for example, in the car seats. We use, for example, spring in spring balances. So springs are used everywhere, right? So in various kind of gadgets, we use spring. For example, I have this flashlight. So when I press it, right, so it now glows because there is a spring which pushes the circuit, the small connection there, and then it completes the circuit. When I push it again, the spring expands and it goes off, right? So before I explain you the theory, I would like to show you a small, simple demonstration, right, which you can do in your home. Okay, so let me move slightly this way so that I can do the experiment, show the demonstration better. Okay, so here you can see there is a system I have set up here with a spring. I found this spring from the spiral band notebook, right? So I'm using all household gadgets. So these experiments may not be perfect, but they help us understand the concept, help understand the material in physics, right? So I have this spring, steel spring, right, which is a kind of stiff spring, less flexible, right? So and I have tied this hand sanitizer bottle, which is about 237 milliliter, right? So if you say that 1 milliliter is equivalent to about 1 gram, so this is about 250 gram in total, let's say, including the material inside as well as the bottle, right? The material of the bottle, right? So what I do is I pull it down, right? I have suspended this. I hope you can see. I have suspended this hand sanitizer at the end of the spring, and at the top of the spring is supported from a rigid support on the table. Okay, you can see that is the rigid support on the side of the table, right side of a table, and the bottom I have tied to bottom of the spring is tied to this hand sanitizer, right? So this system is called mass spring system. Okay, strictly in physics lab it is called vertical mass spring system. What does that mean? Because this is in vertical direction, right? So if you set up this on a horizontal table, so in the lab it is called horizontal mass spring system. Okay, so this system now, it is not oscillating or not moving, so it is at equilibrium. Okay, it is at equilibrium, right? So this spring is very thin, right? It is a kind of stiff but thin, and the mass of the spring is very, very small compared to the mass of this hand sanitizer bottle, right? So we usually neglect the mass of the spring in doing our calculations, right? So to be precise, to get a better result, of course, you can measure the mass of the spring also. That makes a little bit difficult, okay? Okay, so the analysis becomes a bit difficult, okay? So the system is in equilibrium. So what we are doing, what we have been learning since last 2.5 months, almost 3 months, is forces, Newton's laws of motions, like that, right? So how many forces are there on the spring? Please think about and then type in the comments how many forces are there on the spring. Okay, so I'm watching your comments. Could you please type how many forces are present on the spring, and what are they? Okay, so please think about for some time. Okay, so see, we know that there is a force of gravity on any object which has mass. It is acted by Earth's gravity, right? So as I demonstrated in the previous class, right? For example, this object, this ball, when I let it go, it falls down, right? Because there is gravity. Just like that, this hand sanitizer bottle has mass, and roughly about 250 grams, right? I haven't exactly measured, but that is about it based on the quantity in here, right? Okay, so what happens that there is the force downward, and according to Newton's second law of motion, F equal to ma, right? According to Newton's second law of motion, F equal to ma, right? So force, gravitational force is downward. We know that, right? F equal to m, weight equal to m times z, right? That is vertically downward, right? So if we apply F equal to ma, and if that is the only force, this bottle should not be standing there, right? It should be going down in the direction of gravity. It should be accelerating. But we clearly see that the bottle is hanging in there. So the system, in one way, we call it is in equilibrium, right? The system is in equilibrium, right? So for equilibrium, the weight force must be cancelled by some other force. The weight force must be balanced by some other force. What is that other force? And of course, the object in contact with the hand sanitizer bottle is the spring. So the spring exerts a force. And that spring force, or the force exerted by the spring on the bottle here, was first given by Hooke, Robert Hooke, who was contemporary to Sir Isaac Newton, right? So that force is Hooke's law force, okay? And that Hooke's law force is given by some quantity called K times the stretch. How much is the spring stressed? Remember one thing, when I did not attach this hand sanitizer, the spring was shorter, right? Because there was nothing to stress the spring, right? But when I attach the hand sanitizer bottle, because of the Earth's gravity, the weight of the bottle, right, the spring stressed, right? Make sense? Okay. So if this makes sense, right? So the upward force, which is the Hooke's law force provided by the spring, the downward force, which is the weight provided by gravity, weight of the hand sanitizer bottle. So those forces are exactly equal in amount but opposite in direction, right? So the net force is 0. That's why this is in equilibrium, okay? So now what we can do is we can gently pull this down. We can gently pull this down, this mass, okay? Gently pull this down and release. Let's see what happens. You see, it is oscillating up and down, right? You see, it is oscillating up and down, right? So what you can do is applying, right? So yes, I see the comment by some person who is watching, Suresh Giri. Okay, thank you. So F equal to minus kx. That's right. So k is the spring constant, which is constant for a given spring. X is the stretch, right? So when I pull it down like this and then let it go, right? Okay. So I need to release very carefully, right? So when I pull it down and release, it starts oscillating, right? So since this string is a little stiff, it's not much flexible, so it is very difficult to count the time period. So if you would like to do this experiment, please take a little bit flexible spring so that you can calculate the time period. What is that? What does that mean? We already did an experiment on simple pendulum, right? We did an experiment on simple pendulum, right? So where we measured the time period. And it was easier to measure time period in that case, right? Because it had a good amount of period, right? Good amount of oscillation. But here it is oscillating faster. So I tried to time it, but I could not exactly get a good amount of time from while I repeated. So I don't have other slightly flexible spring. So if you have slightly flexible spring, you can measure the time, okay? Right? So what you do is from certain reference point, so count the time for maybe 10 oscillations or 20 oscillations, or you can record the time by using stopwatch. Okay, when you record that time for 20 oscillations, right, if 20 oscillation takes, like, let's say about like 5 seconds, you can find the time for one oscillation, which is 5 divided by 20, right? So that is what is called time period, and that time period is extremely important to determine the characteristic of the spring, that is the spring constant. Okay. So you can do this experiment once once you measure the time period and the mass of the object which has been attached here. I have, for example, in my case, I have attached the hand sanitizer bottle. Okay, so please do this experiment whenever you have free time and whenever you have equipment, right? But now I would like to show you some physics behind it, or some mathematics. From the very first episode of my Physics is Fun, right? I believe today's episode is 12th episode, right? So from the very first episode, I'm telling you that so we need to know mathematics to understand physics well, right? So let's try to understand this system better using some mathematics. Okay. So a couple of things before I switch my camera to other direction, right? So see, when I pull it down, right? When I pull it down and release, so spring pulls upward, right? Spring pulls upward to certain point, and when the spring is compressed, it pushes down, right? So the stretch or the compression are in opposite direction of the force, right? So that is very important thing to understand, okay? And the the velocity, for example, when I pull down and release, right? When it is moving upward, velocity is upward, of course, right? Velocity is upward, right? And so these quantities varies, to be exact, this velocity, force, acceleration in this oscillating system vary sinusoidally, like a kind of sine wave, like similar to our heartbeat our heartbeat may not be exactly sine wave, but like they oscillate back and forth, right? Like a sine wave or cosine wave. Okay. So now let's try to understand this system mathematically. Okay. So for that, what I am doing now is I am turning my camera to a different mode. Okay. So we know that Newton's second law of motion, which is F equal to ma, right? So here we are applying Newton's second law of motion in spring system, and the force provided in Newton's second law, F equal to ma, the force is provided by the spring. Okay. So before I go to the physics, let me tell you about Newton and Hooke. Isaac Newton gave so many physical principles. We know about that, like Newton's laws of motion, Newton's laws of gravitation, some laws in optics, Newton's calculus, which is mathematics, and so much. In the same way, Hooke has also several contribution in physics. One of them is, of course, Hooke's law. Okay, Hooke's law of force. Okay, so they were contemporary, and if you go to the history, what it say that actually they were rivals of each other. Okay, so what is Newton's second law of motion? We know Newton's second law of motion tells us that force is equal to mass times acceleration, right? F is the force, m is the mass of the object, a is the acceleration. So in our case, what we do here is force is equal to minus k. That k is called spring constant or force constant, right? Minus k times delta x. That delta stands for stretch. So delta x means it is not delta times x, it is delta means the difference in stretch, and x hat in the right side. Okay, so let me use my laser. Right, so this x hat means that is the unit vector because the force is vector, right? And so this delta x means the stretch of the spring or compression of the spring, and this quantity k is called spring constant or force constant. And why is this minus sign? That minus sign tells us that the stretch is opposite to the force is opposite to the displacement. If I stretch more, the force, the restoring force, it is also called the restoring force, right? It tries to bring back the spring to original position. Okay, that is the meaning of the negative sign. Okay, so that negative sign is there for some good reason. Okay, so k is force constant, delta x is the stretch, and x hat in the last is the unit vector which has magnitude 1. Okay, so now if you watch very carefully, delta x, that is the stretch or compression, and that has the unit of meter. So force is in Newton, so k must be in Newton divided by meter. So that is the force required to stretch 1 meter of the spring, right? Stretch of 1 meter of the spring, right? 1 meter of the stretch is very large actually, right? So that is k, and depending upon the value of k, if k is large, we call that a large amount of force is required to stretch the spring, and such springs are stiff springs or not flexible springs, whereas if k is small, those are flexible springs. Okay, let's step. Now, so as I mentioned, that F is equal to minus k delta x is the spring force, and it was given by Robert Hooke. Right, so that F equal to minus k delta x is called Hooke's law. Okay, so now since there is a net force, we saw that there is a net force, right, and F equal to ma from Newton's second law. So what we can say that Newton's second law gives an acceleration, right? So from F equal to ma, we can write acceleration, where acceleration is force divided by mass, right? Force divided by mass, and we know the force is equal to k delta x. So k times delta x is the force. If you divide by the mass, then that gives acceleration, right? And the minus sign tells you that acceleration is opposite to the direction of displacement, okay, or direction of the stretch. Now, one thing, so you see in my demo, the mass was oscillating up and down. So when it starts from like the equilibrium point, goes down, comes back to equilibrium point, and comes up and comes back to equilibrium point, that one that one whole cycle is one complete oscillation, right? And so since it is moving in a kind of circular path, like, I mean, it is not exactly circle, but it is a kind of oscillating back and forth, so we can measure, right, angular speed, right? So like, what is that? What angle is traveled by the object per second, right? And that is given by k, square of angular speed is given by k over m. So basically this k over m, right, is nothing but square of the angular speed, right? So we can write that, we can simplify mathematically. If you take square root on both sides, omega is equal to square root of k over m, okay, k over m. So we can go slightly beyond and we can find the relation between time period and k, right? So time period, right, so in one complete oscillation, right, the total angle covered in a circular path in a complete oscillation is 2 pi radians, and if you divide by angular speed, that gives you time period. And then we have found the omega in the previous slide. So you can see that in the previous slide, omega is equal to square root of k over m. So if you substitute that, so we can find the time period. And if we simplify, so we get the k, that is the spring constant, is equal to 4 pi squared times m over t square. Now here, see, everything is measurable. M is the mass which is hanging at the end of the spring. We can measure that. T is the time period. We can measure, as I explained, count about 20 oscillations. But in that case, you need to have some flexible spring, or you can use some scientific gadget like ultrasonic sensors. For example, in the labs, we usually use ultrasonic sensors to measure the time period. But in our homes, we can find a slightly flexible spring and count about 20 oscillations, and then record the time for 20 oscillations, divide the amount of time by 20, then you will get the time period. So that will help you to measure the spring constant, right? So this spring constant quantifies or characterizes what kind of spring are we using, right? This spring constant is very, very important in theoretical physics in other areas. By the way, this spring constant is not exactly applicable only to the spring, but any kind of oscillating system, you can analogously take this quantity like the spring constant or force constant, okay? If you do higher level physics, you will see that, okay? So with that, let me quickly show you, go to some technology, okay? Go to some technology and then show you some simulation, okay? As I introduce first simulation in one of the previous classes, right, you can use this simulation to study springs, right? So here you can see two springs up there, right? You can see two springs. Let's use one spring here. Let's use one spring. Let's use the spring of the left side, okay? Let's make the spring tougher. I can make the spring tougher in this case, right? The spring is tougher now. It is more stiff. And I am connecting now 200 grams mass. Now you see the spring is oscillating here, right? The spring is oscillating here, right? And then you can measure the time period. You can measure the stretch by using, by the way, there is this stopwatch. You can use this stopwatch, like starting from certain point of time, you can activate this stopwatch. And you can also measure the, if you like, you can also measure the stretch of the spring by using a ruler, which is given there, right? So this is a very good source of studying physics, right? If you don't have any physical devices right around you, okay? So now, what can you do? You can see the natural length of this spring, for example. That was the natural length. So before it was stretched, what does that mean? So let me reset So that was the natural, you see, so from there to there, that was the natural length that was before stretch. Okay, so let me slightly increase the stiffness of the string. So that is the natural length, right? So that is the natural length, for example, here, right? So let me unclick that, and then let me put this mass, sorry, okay, 1 second. Let me put 200 gram mass here, right? So what was the natural length? That was the natural length. What was the equilibrium position? That was the equilibrium position. You see right here, that was the equilibrium position right here, right? What does that mean? Before it started oscillating, right, the force, spring force, that is the Hooke's law force, and the weight force balance each other at that time. So then what did I do? I slightly pulled down and released, and it started oscillation. And by the way, here we are considering zero damping. Of course, it starts when we consider air drag, so it slows down and finally it stops, right? Okay, so then what else can we do? We can consider the movable line, right? So about that line it is oscillating back and forth, right? And about that line it is moving back and forth, means at that particular point the extra stretch is zero, so acceleration is zero there, the velocity is maximum. Okay, now we can see a couple of more things here. Okay, so let me go to here. Let me see the vectors, right? You see, right? So when you see the vectors here, what does that mean? What do they show, right? So let me do step by step. Let me remove all these clicks, right? So that is the gravity, you see, right? In the second spring, okay, in the second spring, you see that is the gravity, which is what? This red arrow showing downward is gravity, which is constant. That is the weight of the object actually, right? And then if you want to see the spring force, click on that. That blue arrow is the spring force. Please note the length of the spring force. I mean that you see the blue arrow is being longer and longer and longer. As I mentioned when I taught you vectors, the length of the arrow is the magnitude. So the red arrow remains constant, which means that the weight of the object doesn't change. But what changes? The length of the blue arrow changes. That means depending upon the stretch, the force changes, right? And then you can show the net force, right? See the net force is zero now, net force is downward now, net force is zero now, net force is upward. So based on the net force means the vector sum of the two forces. The vector sum of the two forces mean the gravity and spring force, right? The object has acceleration. F equal to ma. If the net force is upward, acceleration is upward. If the net force is downward, acceleration is downward. For example, let's click on the acceleration. Please watch. See, when the force is upward, do you see that yellow arrow? So that yellow arrow and the black arrow, they are following the same direction. Do you see? Why? Because F equal to ma. Force, like for example, now force is downward, acceleration is downward. Now the force is upward, acceleration is upward, right? But the velocity is, we need to be careful. Velocity is the direction of the actually motion. Now see, when it is moving down, velocity is down. When it is moving up, velocity is up. But even if the object is moving up, acceleration is down. Please watch. Okay? So we need to be very, very careful in the direction of the velocity, acceleration, and force. And at some point, velocity is zero. At what point velocity? Please think about these questions. Before I say goodbye to you, please think about these questions, right? So when is the velocity zero? When is the force zero? Right? When is the net force zero? Is individual force zero ever? Is gravity zero? Is spring force zero? Is the net force zero at some point of time? Is acceleration zero at some point of time? Where is the acceleration maximum? Where is the acceleration positive? Where is the acceleration negative? where is the velocity maximum, where is the velocity zero, right? So you can study a lot of things from this simple simulation or the simple demo which I showed you. Okay, so with that, so let me change the camera mode. So I hope this helps you to understand the mass spring system somehow, right? So if you have any question, please write in. I'm trying to help you, since you are staying home now because of this COVID-19 pandemic. So please try to understand the material which I am delivering. So I have posted these videos in YouTube's also, if you would like to watch later, right? So they are there. Or if you would like to share with your students, right, you can share these videos with your students. Okay, so I hope this helps. Thank you so much. So please give me feedback. If you have any questions, please type in the comment. Okay, type in the comment, or you can also send me a question in my inbox. So thank you very much. See you next time with a brand new episode of Physics is Fun. So thank you. Have a good night.